Welcome viewers, in this video we will see the synchronous motor on load for the constant load with variable excitation. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. Synchronous motor on load. Operation of synchronous motor at constant load and variable excitation. Synchronous motor on load, separate video available, and variable loads are separate video available. This is the third video with constant load and variable excitation. Now we'll see the topic. When the load changes for constant excitation, the current drawn by the motor increases. So from previous two videos, we are able to understand this point. When the load changes, the current will changes. Current will increases. When the load increases, current also increases. That is detail available in the previous video for constant excitation. But here we are going to see variable excitation. But when the field is varied by keeping the load constant, the current is constant. So the motor reacts by changing its power factor. So for constant excitation, when the load changes, motor current increases. But when the field is varied, the constant excitation here is varied excitation means the current is constant, but the motor reacts with the power factor. So here we are concentrating the power factor. The change in field excitation changes only the value of EB. Since the load is constant, the power factor remains constant for the same load. Right? So while changing excitation, what happens? EB will changes, but the load is constant, so the power factor remains constant for the same load. So power in equal to root 3 VL IL cos phi, that is equal to 3 V phase IA cos phi. Therefore for constant load, Pin is constant, voltage V phase is constant, therefore IA cos phi remain constant for constant power. The operation of synchronous motor can be studied under different values of excitation. Right? So here finally what we got, power factor also, power also constant. The power remain constant. Right? For constant load, power input is constant, V phase is constant, IA cos phi also constant. So for a constant power. Now for various excitation, we will see that normal excitation, under excitation, over excitation and critical excitation. First we will see the normal excitation. So here normal excitation means EB equal to V phase, both are equal. An excitation in which the applied voltage is equal to back EMF is called a normal excitation. So under normal excitation, EB equal to V phase. So the phasor diagram is shown. We will see the phasor diagram later. So the resultant voltage equal to V phase minus EB, that is equal to IA ZS. This IA ZS is nothing but a loss. IA lags EB by an angle theta. Angle between V phase and IA is pi. So all these things we will see the phasor diagram. Right. So first case EB equal to V pi. Now see the phasor diagram. So this is diagram A for normal excitation, EB equal to V. So this is V phase, this is EB. It is phase difference between this leading by phase difference between V phase and EB is del. This is nothing but torque angle. How this torque angle we are getting, this previous video, the details are available. So the phase difference of VB and EB, V phase and EB is del. This ER is the resultant. Vector difference between EB and V phase is ER. So this angle is theta, del. So this current IA is available, that is lagging. We already see that in the normal excitation, the current is lagging V phase with an angle of pi. The angle between IA and the resultant voltage is theta. So this thing what we discussed earlier. So this is the V phase. EB is phase difference between EB and V phase is delta. That is nothing but torque angle based on the load. ER is the resultant voltage. Phase difference between these two, V phase and ER. IA, current IA is lagging in case of normal excitation with an angle pi. The angle between ER and IA is theta. So this line is nothing but this line is nothing but constant IA cos pi line. This line is constant voltage V phase. So this dotted line refers V phase, this dotted line refers IA cos pi. Now we'll see the next case under excitation. Diagram B. EB less than B. EB is lesser. Voltage is more, back EMF is lesser. So almost same diagram, but the IA is here, is the angle is more. So V phase, EB, it is phase difference of delta. ER is the vector difference of EB and V phase. Here also current is lagging. IA is lagging with the V phase with an angle of theta. This with an angle of pi. The angle between IA and ER is theta. Right? So here what is the condition? This EB is lesser and V phase is more. Next we will see the over excitation. Diagram C. Diagram C, over excitation means EB is more, V is lesser. See, this EB is more than V phase. This is the V phase reference. There is an angle. So this angle is nothing but delta. This angle is delta. Here EB is more. The vector difference of EB and V phase is ER, resultant voltage. Here IA, current is leading. In this over excitation, current IA is leading with V phase with an angle of pi. The angle between IA and EB is theta. The another one more is critical excitation. In that case it's almost same. EB is almost same with V. So in this case, this is the diagram D refers. IA is in phase with the V phase. There is no angle between IA and V phase. So it is in phase. So first two cases lagging, third case leading, the fourth case critical excitation, it is in phase. Now we'll see the description for this. First one, normal excitation, we saw the description. Remaining three cases, we'll see the description one by one. So the second one, under excitation, EB less than V5. When the excitation is adjusted in such a way that magnitude of induced EMF is less than applied voltage, that is EB is less than V5, it is called under excitation. What happened here? ER increases. That is ER equal to V phase minus EB. ER equal to IA ZS. IA also increases since ZS is constant. IA cos pi is constant for constant power. So the increase in IA causes cos pi to decrease to maintain IA cos pi constant. So cos pi decreases. That is pi is increases. So ER shift. So IA also shift. Right. So here when IA increases, ZS is constant, so that IA cos pi is constant for constant power. The increase in IA causes cos pi to decrease, because in order to maintain that, this IA cos pi need to maintain constant. While increasing IA, the cos pi is decreases. That means pi is increases. Therefore, at under excitation, the current drawn by the motor increases for the same load and power factor is lagging. Because this pi increases, it is lagging. Next we will see the over excitation. Over excitation, EB greater than V phase. The excitation at which EB is greater than V is called over excitation. EB greater than V pi, so that ER increases but in opposite phase. Therefore IA also changes in phase. Now IA leads the voltage by an angle of pi, as shown in the diagram. We already discussed. In the third case, IA leads. Pi changes, and so that IA changes to keep IA cos pi constant. So in the previous case the lagging, here it is leading. Current is leading because EB is lesser, V phase is more. We'll see the fourth case, critical excitation. So in the critical excitation, it is almost the same EB and V phase. The excitation at which power factor of the motor is unity is called critical excitation. At unity power factor, angle between V phase and IA, that is pi equal to 0, or V and IA are in phase, that we already discussed in the diagram. Cos pi is 1. So IA decreases to maintain IA cos pi as constant. At unity power factor, current drawn is minimum. So at this it is minimum. First and second case lagging, third case leading. Now it is minimum. Current drawn is minimum. So in this video we discussed the constant load with variable excitation. 4 different cases: normal excitation, under excitation, over excitation, and critical excitation. We discussed the phasor diagram and description. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. All the best for your examination.